So I'm going to talk about a contrast between Enceladus, Europa, and Io. We've done this with a group of, they do the work, I do the kibitzing. There are observed plumes on these three bodies, but also on Triton and Earth, but I'm going to ignore bodies like Triton and Earth and concentrate on plumes into tenuous or negligible atmospheres. These plumes obviously can be sampled and sensed to diagnose the source materials and the conditions that we don't see. I want to concentrate on what physics matters to a plume or what we see in a plume or in a plume model. And since I come from an aerospace engineering department, I'm going to try to relate this a little bit to rocket plume flows. Just sort of to point out a couple of the issues, or several of the issues. If we have a mustard-colored planet with a vent exhausting into vacuum, things that we don't know much about are what's below the surface. We do know the planet radius and surface gravity well. The key thing of what that plume appears like and does are the surface vent properties of gas and particle densities, velocities, temperatures, species, perhaps turbulent fluctuations, the vent geometry, and so on. We can abstract some of the finest details of what happens down here up to a higher level, which we call a virtual vent, which is some trivial distance above the actual surface of the planet, a distance small compared to, say, the diameter of the vent. Typically, what we've been detecting have been particles moving up, generally in perhaps one sort of plume, and gas plumes that are perhaps spatially distinct from the particle plumes. And once the plume is above the surface, plasma flow, electromagnetic fields, and sunlight can affect the plume. We might describe a lot of possible non-dimensional parameters to describe a plume, like a Mach number. I want to set a stage here and say Mach number is a ratio of a local flow speed to a local speed of sound. It's not necessarily, you can say I have a plume of a certain Mach number, you're probably talking about the Mach number at the vent exit plane, but in general, Mach number is a scalar throughout the field. Reynolds number is a ratio of the momentum to viscous forces. Knudsen number, which I'll talk some about today, can be made up of Mach number and Reynolds number, and it's a ratio of mean free path to some suitable flow scale length. Again, this is a scalar that varies throughout the flow. We can talk about a particle mass loading, a turbulent intensity, a Froude number, which kind of tells us how high the plume goes, a pressure ratio of the exit pressure divided by a background pressure, which for us today is going to be generally infinity, various geometric parameters describing the vent region, parameters describing particle size distribution, and others. In this eye chart, I want to highlight some of the differences between Io, Europa, and Enceladus plumes. Their primaries are Jupiter, Jupiter, Saturn. The sources, though, are Io's source is generally hot lava or lava impinging on a sulfur dioxide ice. These two are somehow liquid water. I'm assuming the Europa plume exists, so let me go from there. The plume materials are different. On Io, it's sulfur dioxide and its daughter species. On the other two, it's water and its daughter species, and other things have been detected on Enceladus. Surface gravity is clearly different. We're going from high to very low. That influences whether the material erupting can escape or not. Here, it definitely can't escape. Here, you kind of wonder, but we think, no, it can't escape. And here, it definitely can escape. The source vent shapes, here, it's somehow hot sources, calderas, lava fronts, and so on. Very complicated, and some of them measured or observed shapes. Here, well, it's not clear what the shapes of the vents are. Here, it's clearly the tiger stripe regions, long crevasse-like stuff. All of them have some measure of time variability. Io, seconds to minutes, but some plumes are kind of stable over the years. Europa, well, sometimes it's there, sometimes it ain't. And there are seasonal and diurnal variations, and perhaps even minute scale variations on Enceladus. We can talk about the plume structures. I'll do that. I'll leave this off for now. And the fate of the effluents on Io. They rise, they fall, but then the volatiles revolatilize and form Io's atmosphere. On Europa, it's not obvious what happens to those effluents. On Enceladus, all the gas essentially, and many of the grains escape. Some of the grains fall back. Let's talk about Io. That's a cool movie of the Tvashtar plume. Pele forms this, and Pele-class plumes form the big rings. I'm going to talk about Pele-class plumes mostly today. We imagine the plumes as arising from something like this. I didn't download Hawaii stuff yet, but our imagination is that this is the Nyiragongo caldera activity with lots of little presumed gas sources, perhaps more near the surface, but spots and lines. And it's just that this is only a few hundred meters across, whereas the hot areas observed near Pele that's a 30-kilometer scale. So maybe this just much bigger is the way we view things. And we use the direct simulation Monte Carlo method, which is a stochastic model where we exhaust particles from a vent. Particles can be molecules or grains. They move through space ballistically. They follow elliptic trajectories, and they collide with each other. The molecules can collide with the grains. We can also include, and we do, include chemistry, many species chemistry. It's coupled to a radiative transport code. And so we capture a lot of the non-equilibrium physics that occurs above the ground. So back to this hot distributed caldera region of Pele. From Bob and Rosalie, there's this thermal map which we digitize, and this is our source region. So our source region really looks like all these spots, this archipelago of sources. And so kind of a question is, how do you go from all these little dots and splotches here to the giant umbrella that is the Pele plume? So from this hot region, we abstract to this archipelago source region at what we call a virtual vent height of we actually use 700 meters, so just above the surface here. And then we generate particles where all the black spots are and move them upward. What does that do? And the reason I'm talking about Pele, and this is in the cryo plume discussion, is because it illustrates pretty well some of the exotica which can happen above a complex source. So here's our complex source region. I want to concentrate on what comes out of source region E. So it's like that. I'll get back to what comes out, what happens when we look at everything. So this is source E blown up, source alpha, beta, gamma, delta. Here, this is a cross-cutting view. These are number density contours. And what you see is the plumes don't just come out and keep going. They interact. And so all these lines and so on happening in these density contours are plume-plume interactions. Those are shock waves. If I slice the flow here at an altitude of 3 kilometers and look down on it, these are density contours, and you can see all these elongated structures, which are the plume-plume interactions, shocks. This is just a tiny, tiny region in the big plume. So if we look, it's above that, and now if I take that and I zoom out a little bit, so now our domain extends up to 20 kilometers, that region I just looked at was down in here. Now you see all those other structures also have plume-plume interactions. So as we step up in the plume, it's a sequence of more and more distant interactions characterized by a whole bunch of complex shock waves seen in density contours or in looking down on the top here at 20 kilometers altitude, or in temperature contours. So you see some very high temperatures along these shock fronts. These are temperatures looking down on the top at 20 kilometers. Now I back out again. Now the domain is at 60 kilometers, and you can see the biggest source region is starting to dominate the flow in density. And if we can look at it with west to the left or with north to the left, and they look kind of different. And this is what happens looking down on the flow at 60 kilometers altitude. And finally, if we look at the full plume, you get the picture of how all that detailed structure has evolved into this giant umbrella. So this is now 300-something kilometers high, and the overall flow is dominated by this giant umbrella structure with a canopy shock at the top, where the uprising gas goes up, becomes quite rarefied in here, then it passes through a shock wave that slows down, the density rises, it starts to fall back on itself, and that's what sustains the shock wave. In the temperature, you see the shock wave is a hot region. This is a very hot region here, but that's a highly non-equilibrium, thermodynamic non-equilibrium region, as different streams of gas are passing through each other. Okay, so that was hot, this is cold. Let's talk about Europa a little bit. The sources we view as quite different. We think that the source, or we're modeling the source as being some sort of rocket plume-like problem where we have some chamber below the surface of gases and particles coming up, and in some fairly near surface region there's a constriction which we call a throat. This is the cartoon out of Wikipedia of what happens in a rocket nozzle, where the flow is from left to right, and density falls through the throat as Mach number rises, and temperature falls, and pressure falls. And then out here, the flow is high Mach number. So in a rocket nozzle, what you see out here is completely determined by the stagnation pressure, or the stagnation conditions in this plenum here, and the area ratio of the throat to the vent exit area. So if I turn that on its side, our cartoon view is that we have a cavity below the surface, boiling water producing vapors at near triple point conditions, and perhaps particulates. That stuff rises up through a constriction somewhere where the Mach number is just 1, and then when it passes out through the vent, everything expands rapidly to very high Mach number. For Enceladus, we're going to talk about, for Europa, we're going to talk about round plumes. Wow, am I slow? I'm going to talk much faster now. So we have examined several different Mach number conditions determined by vent to throat area ratios. We've also looked at a high mass flow rate case, which just is much bigger. And so these are all at mass flows of about 10 kilograms per second, and that's at about 1,000 kilograms per second. And so the difference is when we have low mass flows, what we see in terms of a plume structure doesn't change a whole lot with Mach number. That is the area ratio of vent to throat. But when we have a high mass flow rate of about 1,000 kilograms per second, now the plume looks like a EO-class plume with a big canopy shock. And we think this is more in line with what was probably observed by HST in terms of the mass flow obtained, the height of the plume, and the column densities through the plume. We model photodissociation in the plume, and we get H's and OH's that recoil. If you have the recoil velocities are high, and so particles generated by photodissociation in the bulk of the plume, if the density is not high enough, they just blast right out from the center, and you get a big diffuse structure. On the other hand, if you have enough water vapor in the plume, those particles of H or OH are constrained within the water vapor plume itself. And so they don't get out, and they track the water vapor. If we put particles in the flow of different sizes, in the high-density plumes, which we think is the more likely one, let me just concentrate on that. The particles, the grains are accelerated with the gas because they're collisional with the gas near the vent, and they come up to the gas speed. But then particles of these sizes are not really collisional with this very low-density gas, even in the canopy shock. And so the particles rise higher than the canopy shock. And so you get grains in our model being higher than the gas flow. I'm going to skip the summary. I'm going to have a sequence of summaries. Let's talk about Enceladus. Enceladus is not bigger than Texas. We've seen some of these images before. The source region for the Enceladus plume is probably these tiger stripes, which produce some combination of sheets and discrete jets. Our model is using collisional gas dynamics in the near field, and then in the far field, when the flow becomes free molecular, We can model that with simply a ballistic model in a rotating two-body system. I don't have to talk about that today, but we take these and we put them near the south pole of Enceladus, and then we fly Cassini through it and compare to the observations. Let me concentrate, though, on the physics. Our physical model that I'm going to talk about today is a lot like the Europa model with different vent sizes and throats that we've examined. And it's all in the vent-to-throat area ratio in our model. That is, if the area ratio is not too big, the Mach number is small. If the area ratio is big, the Mach number gets bigger at the exit. I'm going to skip this more complicated vent model. Let me talk about the gas dynamics in the near field. In that model of an exhausting plume into vacuum, the density and temperature and pressure drop very rapidly. So therefore, the supersaturation ratio of the local pressure divided by the vapor pressure becomes huge. This is a log of that ratio. And so one expects condensation in this near field. We can model that condensation by starting with grains that grow due to collisions with the gas. As they move up, they grow a thin shell of thickness delta R. So we find that as the Mach number of the vent decreases, the grain radius delta R increases. That shell thickness doesn't depend on the initial grain size, but it is proportional to the size of the vent. However, the grains stop growing at a certain height because there's not enough gas to collide with them and make them grow. And so this is the normalized collision rate, normalized to the collision rate between gas and grains at the vent. And you can see it falls exponentially. And so by the time one gets within about 10 vent diameters, almost all the growth of the grains has stopped. So that allows us to conclude that the flow is very supersaturated above the vent. Condensation is very likely, but is confined to the very near vent region. And so if the vents are of scale meters to tens of meters, then condensation alone is not sufficient to produce the micron-sized grains that CDA observed. And so something else must produce those grains of that size. The grains are fully coupled to the gas flow near the vent, but they decouple within a few tens of vent diameters. That is, the grains and the gas are moving independently of one another within a few tens of vent diameters. And so if you want to, you can't infer anything about grain motion or gas motion by looking at the grains with the Cassini data. You're just not looking close enough. We have examined things like the mass flux ratio between the grains and the gas, and the vapor, the ratio of velocities between the grains and the gas. And those are important parameters to determine what you see further away. I'm going to skip going over those details, but suggest that when the mass flow ratio is high or the velocity ratio is low at the vent, the effect of the grains on the gas is substantial. For plausible mass flow ratios, probably less than 1, the grains have minimal effect on the gas unless the velocity ratio is small. And I've already said some of that. Let me point out, though, that there are a lot of parameters one could put in to do these kind of simulations. How do you deal with that? DSMC, which most people don't want to learn, is an expensive way to do calculations. Each one of these simulations is hundreds of hours on a workstation. Okay, so, and our nominal situation is roughly about a 1 to 2 meter size vent with mass flows like that and vent speeds like that. And they're cold, and we looked at grain sizes. What we've now done is we've completed a sort of vast parametric survey of parameters like that, where we have systematically done hundreds of DSMC simulations where we varied the vent radius about a nominal value. We varied the number density in the flow about that nominal value, the gas speed, the ice speed, the ice to gas mass ratio, the flow exit angle, the ice grain size, and the temperature. And at the top of where the flow goes non-collisional, we've now extracted profiles of density, temperature, velocity, and macroscopic properties. And we fit that with a curve, and we have created parametric representations of those curves that we're hopefully going to get through Icarus in the next few weeks. So here are, for example, for the nominal case, that's how the density falls off with distance from the axis. Here's how the speed varies in one direction, the speed in the other. and these are the similar grain properties. And we fit those with different polynomials or exponential of a higher order polynomial and tabulated those fits. And so now the community doesn't have to do DSMC, it can just do free molecular calculations, which is ballistic, can use these fits and combine, and it works great. And so, for example, we've systematically varied the gas speed, and we get different, depending on what gas speed we put in at the vent, we get different speed distributions or density distributions. We fit them with like a log of the number density and a polynomial, and that's the fit, say, versus Mach number or versus exit speed or versus particle number density ratio and stuff like that. And so now you can use A, B, and C, which we tabulated, to reconstruct, for example, some off-nominal condition. And this is conclusions and advertising on that last part. I hope that for people who are trying to back out like Enceladus vent conditions or subsurface conditions, you can now fit to the Cassini kind of data and do that. I'm out of time.
Well, I think looking at the unary system H2O, which your work is dominantly looking at, is the obvious, clear place to begin. But we know pretty for sure that on Enceladus, and we can speculate maybe also Europa, that it's other gas phases that are exsolving out that are driving the plume. And so do you plan to get into like H2 powered?
So we've run H2. And H2 is very interesting. I disagree. I don't think it's the other species driving the plume. Our model is it's the boiling of the water, and the other species are moving along with it mostly. We can argue that. We've run H2. The interesting thing suggests there had been an early observation that the gas flow is moving at about 1,700 meters a second. That's more than the kinetic energy that's allowed by the ultimate speed of expansion of water vapor into vacuum, which is about 1,000 meters per second. So we examined, well, maybe it's just there's H2 in there that the gas that lets you accelerate to higher speed. No, that would take way too much H2 to do that. We've also examined whether H2 can separate from the water vapor, and yes, it can at the edge of the plumes. That is, the H2 diffuses out of the plume in essence at the edge. We've also examined what happens to H2 below the surface in one of those long conduits, and whether it can separate out from the water vapor below the surface, and that's pretty interesting.
Sounds like you've got another talk to give.
Okay. Kendi, are you willing to? Another day.
So I would say that to address both of you, because this is kind of relates to both, I think the inputs will be very different if you set up a conduit flow scheme, because you're really explicitly solving from a different starting point, let's say, than the way that my model works. The H2 will drive the conduit flow, most of the processes are going in there, and will provide very different inputs into a DSMC model. And so I suspect, I'm excited to be able to perhaps, once I get this paper published, provide you with quite different inputs into your model. And I think we'll find some interesting additions to the parametric space. And I really do like your parametric space idea. I think it will make your work far more usable to the bulk of the community. But the other thing I will say is your vents, I personally think they're quite large. They certainly would be for mine, and I would be cautious in interpreting Jay Gogan's work as suggesting there are 10-meter wide vents. 10-meter wide vents would support pretty massive mass flux.
On Europa or Enceladus?
And Enceladus.
So our nominal is 1.5 meters.
Your nominal is, but you also pointed at Jay suggesting 10, and I don't think that's what he said. I think he says it's a hot surface that's emitting that's 10 meters wide, which is perhaps a little bit different if there's conductivity into the surrounding ice. But I would look at much smaller vents as well. Just expand that range down a little bit.
We have. When we go to very, very small vents, now everything sort of looks the same with vent size until you get to the point where the gas where Knud's number effects at the exit become important. That is, once the vent becomes less than about 100 mean free paths across at the exit, then other rarefied flow effects occur. But otherwise, the point is whether the expansion occurs in the continuum regime and you can get all the energy out of the gas before it expands to Mach infinity, or whether it retains internal energy out to rotation, vibrational energy out to, and you never get that back.
Yeah, well, in my case, the nozzle can go quite a long way down below the surface, can be very overpressured, and you can still be in a liquid-dominated regime. And it's a very different kind of inputs, I think, to your model.
Oh, hand me a boundary condition, and I'll run it.
I will do.
So I was interested in the plots that you were showing about the distributions of particles in the different plume simulations. And I'm thinking, if we get to Europa with Clipper and we don't see active plumes, but we find deposits of particles that are either diffuse of certain sizes or annular of certain sizes, I was trying to figure out from your slides what kinds of useful information we can back out of that.
So I was talking to Lene yesterday. We have done the Pele plume in detail, where we have these beautiful maps of red rings and the dark deposits inside of that and some light deposits. And so we did a sequence. The way we approached that, if you see stuff, you can back out then what the grain size distribution was. So what we did was we did a sequence of simulations with the coupled gas and grain dynamics for 1 micron grains, and they go up and they fall down, and they form what we call the basis function on the ground distribution. Then we do 2 micron grains and 3 and out, and then we can do a fitting from the photographic observations to figure out how to reconstruct the size distribution at the vent. And so from that, we were able to argue that it's made up of 2 log normal distributions, probably from 2 different physical processes. One process, we call that our oatmeal model, which is you get 2 size distributions out of boiling oatmeal. I was told to use grits here. You get one due to the spatter of the grits and the other due to the condensation of the vapor in the bubbles. And so you get, presumably, 2 physical sources for particles. So that's very doable, but you got to do these forward simulations to do that.
Mm-hmm.
That's pronounced grits. Okay. Quick question. So this virtual plane, the reason for that is
so for Pele, we did very detailed models. We did a bunch of simulations at 1 centimeter sort of right. I showed those movies of Nirangongo. So we did simulations all the way down to the hot lava at centimeter scale of many of those, and then when those undergo jet-jet interactions, and then at a certain height, all those little things sort of merge together, and so we take that as the height of the virtual vent. So we go up several little vent diameters, and so long as those little vents are small compared to the size of the entire caldera, we choose to ignore the tiny vent interactions.
okay. And so you assume temperatures from
expansion from
the
lava
Galileo
surface
data,
out
and a mass flux is a parameter.
mass flux is a parameter.
Okay. All right. And just one quick question related to Jeff Collins. Do you predict how much solid or ice particles fall back onto Enceladus, or is that a function of assuming a gas to particle ratio in the beginning at the source?
It's a function of several of the parameters. One is the size distribution of the grains. One is how well coupled the gas and the grains are at the vent. One can argue that the gas should be moving faster than the grains at the vent, as you've seen in the literature. There's other ways you can get it to go the other way. And so it's that slip ratio. And the third key parameter is the mass flow, the mass loading. Do you have tremendous amount of grains in the gas or not? I know there's low-speed grains that come up and fall down right near the crevasses, but there's also high-speed grains which get away. And so you can make both happen, but you just have to choose the boundary conditions right.
Okay. I'll talk to you.